So now, today, what we are going to talk about is interacting systems. It is in no means it's going to cover all possibles of possible interacting systems, but it is just to give you a flavor of how you treat interacting system. Even to this extent, we are going to consider weakly interacting. Now, so far in all the systems that we have considered, particularly in the canonical ensemble as well as in the macrocanonical ensemble, we considered all our particles to be non-interacting. So that the advantage was in the canonical formalism, we could write down then partition function Zn is equal to q to the power n divided by n factorial. The n factorial essentially was because of the indistinguishability of the particles, and q to the power q was the single particle partition function. So hopefully you will recall all these details. But in real life, ideal gases and ideal things are really ideal in the sense that they are just a model that we can do on pen and paper. It gives you a nice feeling that you have an analytical result, but in real life things are very difficult. You have interacting systems with particles interacting with each other. So the idea is, how do we treat such things? So we will take the example of a hydrostatic system. For example, a gas of n particles, and each of these particles interact. There is a pairwise interaction between these particles. We will call them, let's call V of Rij. Now usually, mostly this pairwise interaction is typically either taken as a hardcore, which again gives you certain advantages, or is a soft core. A hardcore potential is if you plot the potential as a function. So let's say you place this particle, ith particle, and this is the distance from the center of the ith particle, and you are plotting V of R. You say that there is a certain size of this particle, so therefore we will say there is a certain size of this ith particle, and no another particle can come and sit in this inside this volume. So essentially we say that the potential is infinite. It's infinitely large, high, so that you cannot have any kind of penetration in this part, right? Clearly, so Vr is infinity for r less than sigma. We will say that the size is sigma and is 0 otherwise. This is one type of modeling, and this is typically called a hard sphere system. There is an advantage over here because effectively your potential goes to infinity. Therefore, you see, in the canonical ensemble, we always used to write e to the power minus beta v of r. But then, since v is infinity, beta doesn't play a role. So such systems are typically athermal, which means all the properties that you see does not depend on the temperature, but rather it depends on the volume fraction of the particles. Now, the second type of interacting systems that people typically model are what are called soft core. For example, one of them is what is called Lennard-Jones potential, and that is sigma over r to the power 12 minus sigma over r to the power 6. There are various modifications. They are also called mn potential, with this being m and the n being 2m. So this is the repulsive part, and this is the attractive part. So the generalization can be this, but these are all generalizations of this. But the bottom line is, if you plot now, you see this part, the potential has a minima, this potential has a minimum at r is equal to 2 to the power 1 by 6 sigma. Not exactly sigma, but sigma. So this potential is very steep, but it shows a attractive basin and then vanishes. And this is where it's 2 to the power 1/6 of sigma. Now this is a soft potential, right? Here, of course, your temperature will play a role. You will have a phase transition, or all the properties will depend on the temperature of the system, unlike your hard sphere. So the question now is, how do you handle such a thing? So let's start, and our starting point again is the n particle Hamiltonian, which is given by sum over I pi square over 2m plus ij, I less than j. This is the interaction, and we will call this as v of rij. Before we go further, we define a function e to the power minus beta of v rij minus 1 as f of rij. The alternative notation that we are often going to use is, instead of f of rij, we will write them as f of ij. But that comes later on. Good. So we have this interaction. And clearly you see that I am considering only pairwise interaction. So there is only pairwise interaction in the system. I mean, you can cook up any more complicated interactions, which 3 particle, 4 particle interactions, but it suffices for us to consider such a simple system. Let's calculate the n particle partition function. The n particle partition, canonical partition function, is 1 over n factorial 1 over h to the power 3n, and if you have forgotten how this comes, the n factorial comes from the indistinguishability of particles. This factor is essentially to make Zn dimensionless, because after all, kBT ln Zn is going to give you the free energy, and then of course you have d of xn e to the power minus beta h, where this vector is now the set r1, r2, rn, p1, p2, pn. If I work it out explicitly, I have dr1, dr2, drn integral dp1, dp2, dpn, and then the Hamiltonian is sum over I pi square over twice m minus beta, and then you have minus beta I less than j v of rij. Right? Now this is the part which is doable. It's essentially product over I dp I e to the power minus beta pi square over twice m. So it's 3 integrals, and I know what this is going to give. So I can immediately write down this as this h to the power 3n is going to, so this is going to be 2 square root pi by a. Each of this integral is going to be pi, and then a is going to be beta twice n pi 3 by 2. There are n such particles, so you're going to have 3n by 2. So this integral is going to be 3n by 2. So I'm going to have 1 over h to the power 3n twice m pi over beta raised to the power 3n by 2 integral dr1 dr2 drn is e to the power minus, then we continue with this ij v of rij. This part we are already very familiar with, and this takes the form 1 over n factorial 1 over lambda t raised to the power n, where lambda t is the thermal de Broglie wavelength, thermal de Broglie volume, and I have dr1 dr2 d of rn e to the power minus beta sum of I less than j v of rij. So there is a double summation I comma j as well as I less than j. Now lambda t is lambda t whole cube, where lambda t is beta is going to be beta h square over twice m raised to the power 5. We can recast this so that things are familiar with our ideal gas result. We write this as v over lambda t raised to the power n and 1 over v to the power n dr1 drn e to the power minus beta sum over ij I less than j v of rij. If you expand this sum, you see this becomes v of r12, particle number 1 interacting with particle number 2, then you have beta of v r13, so on and so forth, and all of this factor out as beta v r12 minus beta v r13, so on and so forth. Now recall we had defined the function beta of vrij minus 1 is going to be f of ij. So clearly this means I can use this to rewrite e to the power minus beta vrij as 1 plus f of ij. So I have 1 plus f12, 1 plus f13, all possibilities, so that this becomes product over pairs 1 plus fij. So the canonical partition function then takes the form 1 over n factorial v over lambda t raised to the power n 1 over v to the power n dr1 drn product over pairs 1 plus f of ij.